In this video, we're going to take a look at the normal distribution. So last time we determined the likelihood of case successes and end trials, and we were using a binomial distribution to do that. And that was discrete. But what will we do if we can't count the number of successes? So for example, how do we calculate the probability that someone has a body temperature between 98 and 99 degrees Fahrenheit? That's continuous, that scale, right? So how do we go ahead and do that? So before we get to answering that, let's first remind ourselves of some of our earlier terminology and symbolism. So we want to label each of the following values in the example using proper notation. So the average weight of all cats is 54 pounds with a standard deviation of 10 pounds. And John has a sample of 2 cats with an average of 13 pounds and a standard deviation of 2 pounds. So the first thing we want to notice is that the average weight is applied to all cats, and that all cat statement means that this is the population. Okay. And then the average weight that's calculated and the standard deviation for that population data means that these are parameters. And for parameters, the symbols for our average or mean is going to be mu. So mu is equal to 54 pounds. And the symbol for our standard deviation for the population, that parameter, is sigma, and that is equal to 10 pounds. Now, John has a sample of 2 cats with an average of 13 pounds and a standard deviation of 2 pounds. That is therefore a sample, so it says right there, sample, which means then that this average of 13 pounds and the standard deviation of 2 pounds, those are statistics. Statistics, since those measures came from the sample data. All right, and the symbols that we're getting for this one, we have N, our sample size is 2. Our average or mean as a statistic is given the symbol wide bar, and so that is going to be 13 pounds. And our standard deviation for the sample is going to be the symbol S, and that is 2 pounds. All right, so just a quick reminder on those things. Now let's take a look at the normal model itself. And we say model because most of the time we're going to collect data and see a histogram, which is a display of the data in a more discrete looking fashion, those blocky rectangles, right? And the normal model is something we apply to that to give it a smooth curve look, okay? And so we're basically covering up our histogram with a smooth curved surface. In order to use the normal model, we're going to need to be assured of some certain conditions before we get to use it. And the biggest condition is that we observe a distribution that is unimodal and symmetric and looks kind of like this bell shape we see right here, right? So we want unimodal and symmetric, modal plus symmetric data. Symmetric data can have a normal model approximation. Okay. All right. So in the case of cats, we might collect some more cat data. How did they come across those parameters to start with, right? We had a whole bunch of data collected, and then it started to display itself in this shape. Perfect. So we're going to throw a blanket over top and we get this nice smooth curve. We're going to approximate the data we collected on a large scale and represent it in terms of this nice smooth curve. Okay. Now there's a few things that are awfully special about this normal model or this bell-shaped curve that we're seeing right here. First of all, we know that the population mean, or whatever we're talking about for our center for the model, is going to be mu. So it's going to go right in the center of that picture. And then we can go above and below that by certain numbers of standard deviations. So this might be mu plus 1 standard deviation, mu plus 2 standard deviations, and so forth. We could go 3, but this continues off indefinitely. So the curve itself is going to go off to positive infinity, and it's going to go off in the other direction to negative infinity. So the curve itself is infinite, regardless of the measures that it is representing. So if we were doing weights, clearly weights don't go into the negatives, but our model for that distribution still will. The normal model itself will keep on going. And that's important to recognize because under the curve, this whole space here That area is representing probabilities because it's the frequency, right? We can effectively kind of imagine this still as a blocky histogram, and those heights of bars, those are telling us how frequently the data is coming up, right? And so all of our data should be fitting under that curve, which makes it our area coverage, the probability is going to have to equal 1 under that whole curve. So the area under the curve of a normal model, or any model really for that matter, is equal to the probability, since it is illustrating the frequency or likelihood that you're going to have those different values come up. And the area under the whole curve, so from negative infinity to positive infinity, is going to equal 1. So 100% of our outcomes are going to lie under that curve. So when we do normal model probability calculations, what we're doing is finding the area under the curve between two of our values. And the values themselves, right, that's what lies on the axis, the horizontal axis. These are the actual data values, and then the heights in this picture are illustrating the frequency of those values. And so we'll see that the highest height is going to happen around the mean or the center. Most of our values are going to be there. Okay. And then we'll have less and less frequency as we move away from the center position. Okay. That's some of the main characteristics of this model. So the standard bell-shaped curve is unimodal and symmetric, and that is what we refer to as the normal model. And we primarily use normal models to approximate a population distribution. So we describe its mean using the symbol mu and its spread using the symbol sigma. Okay, and we define the distribution. So to define the distribution, we want to give all the information that's needed. So namely, what is being distributed in that picture, in that illustration? Well, what we're illustrating is the frequency of our data values. And so for our cat example, it would be the weights of all our individual cats. And so we give that label the label Y. So that's what's being distributed. And the shape of that distribution is going to be normal, and that's what the uppercase N represents. So this is normal. And for a normal model, we then need to specify two pieces of information in order to proceed with the rest of our calculations. All other calculations can be done knowing just these two other pieces of information. Just like with the binomial distribution, all we needed there was the number of trials or sample size and the probability of success. And we could go ahead and make tons of different calculations of probability, expected value, standard deviation, just with those two numbers. So for a normal model, our needed two numbers are mu and sigma. So provided we know the mean and the standard deviation, we're golden. We can do all kinds of calculations with just those pieces of information. All right, and the other thing to notice here is that mu, sigma, order matters. Okay, we always list this in order with the mean before the standard deviation. Okay, so that's the basics of it. Let's take a look at some other information. Now, the normal model, we've talked briefly about the idea of frequency and that most of the values are going to lie around the mean. And this is the other rule that kind of gives us a little bit more specifics about that. So the 68, 95, 99.7 rule, it's going to give us the frequency distribution basically for our model. So something you may have noticed in the distribution we drew is that the values closer to the center are more likely than those on the edges. And in general, areas under the curve correspond to the probability of events. So we have two approaches for calculating those probabilities. And the first is the 68, 95, 99.7 rule. And that rule states that approximately 68% of the data under the normal curve is going to be within one standard deviation of the mean. 95% will be within two standard deviations of the mean. And 99.7% of the data will be within three standard deviations of the mean. So this is actually pretty cool. It relates back to what we were talking about before in our interpretation of the mean and standard deviation together. Together, they're telling you that most of the data will lie within one standard deviation of the mean. And this is one of a couple rules that comes from. So if we are looking at this picture still, Okay, this is where our mean lives, is right in the middle. It's the most likely outcome in our bell-shaped curve. Then we could go mu plus a standard deviation, mu plus 2 standard deviations, and let's call that 3. So mu plus 3 standard deviations, and we go back down, and that's minus 1 standard deviation, mu minus 2, and mu minus 3 standard deviations. And so what this is saying is that within 1 standard deviation of the mean, we will obtain 68% of our data. So between here and here, so that's within 1 is always going to mean above and below by 1 standard deviation. Okay, we're going to find 68% of our data. And so our data being the actual data values in our population, or at least at this point, we're thinking of this distribution as the whole population. And then we're going to see 95% of our data values within 2 standard deviations, so 95%. And then we're going to see within 3 standard deviations, we'll get 99.7% of our data, 0.7% of our data. Okay, now this again corresponds to a few different interpretations that we've seen so far in the class. And so first one is that most data values will be within 1 standard deviation of the mean. Okay, and so we can see that most is definitely going to include 68%, right? The majority of our data values are within 1 standard deviation of the mean. The other thing that we connect to this idea is that we also have the idea of unusualness, right? And we said that values are considered unusual when they're more than 2 standard deviations from the mean. And we associated that with z-scores. It turns out, right, these points that I've added here, if we think of this in terms of a z-score scale, z-scores, this would be 3, 2, 1, 0, -1, -2, -3. So when we're talking about unusualness, we're also kind of looking at this picture and this idea. 95% of our data is going to lie within 2 standard deviations of the mean. So it's unusual if you're more than 2 standard deviations from the mean. There's only a 5% chance that your data will lie outside of that, or at least in the normal model scenario. So the other one then is that we have, unusual, let's try and get that away. Unusual if more than 2 standard deviations from the mean. And again, if we look at our picture, 95% of our data values are going to be within 2. So yes, it would be pretty unusual. There's only a 5% chance that you would be outside of that. And so that's a connection to our labeling of unusualness for our data. All right. So let's take a look at our cat example. So recall that the weight of cats is normally distributed with a mean of 54 pounds and a standard deviation of 10 pounds. And we want to first show a sketch of the distribution showing the 68, 95, 99.7 rule. And this is a phrasing on questions that comes up pretty often. And so I want to demonstrate what is expected for that type of question, what you should be responding with. And what you want to do first is draw a picture of the normal curve, that bell-shaped curve. Notice that when you're drawing it, it is not just a singular hump. It goes from concave up to concave down and back to concave up again. So there's some of that swooshing that goes along with it. And you're going to be drawing a lot of pictures of this, so you'll get better at it. I'm just going to make this a little... I am going uphill on this every time I seem to draw it. There we go. And there, that's a little bit nicer, a little bit bigger. Okay, and so we want to show the 68, 95, 99.7 rule. So we want to, across our axis, our horizontal axis on the bottom, have breaking points of 1, 2, 3 standard deviations from the mean. Okay, so there's our center, and I'm going to draw actually a full line because I want to break this down a little bit more than usual. And that was 54 pounds is going to live there. Then we're going to go 1, 2, 3 standard deviations above and below, and using the actual data itself as opposed to just labeling +1, +2, +3. We're going to put the actual data values there. Okay, so we'll go 1, 2, 3, 2, 3. One standard deviation from the mean is usually going to occur approximately where you change from concave down to concave up. And then this is standard measures on a number line. So your next spacing should be approximately the same as that first one. And don't get too caught up with these. It's okay. We're doing sketches. I'm just trying to do the best we can with them. All right, so the standard deviation was 10 pounds, so we're going to go up by 10. So that will be 64, 74, 84. And make sure you're labeling these pictures with what you're measuring across that axis and what its units are. So these are weights, and those are in pounds. Okay, and then we'll go down by the same amount. So 1, 2, 3 standard deviations. So that's going to be 44, 34, and 24. And I'm going to again put those lines in there. Now what you're needing to show for the 68, 95, 99.7 rule is really just these general statements that between here and here, we're going to have 68% of our data. Between here and here, we're going to have 95% of our data. And between here and here, we're going to have 99.7% of our data. But what I want to do in here is just give a little bit more detail to that. So in terms of these frequencies, there, we'll clean that back up. I want to break those down a little further because we want to be able to calculate probabilities. And so if we can make each of these regions assigned a probability or likelihood, then it'll make those calculations a lot easier. Now, if I know that between positive and negative 1 standard deviations from the mean, I have 68% of my data, then that means due to symmetry, I can split that in half and say that there's 34% in each of these sections, okay? Because that needs to add up to 68% altogether. Then I can go, all right, well, how about I know that between -2 and +2 standard deviations from the mean, I'm going to have 95% of my data. So I can take 95 and subtract the 68% that I already know, and then I'm left with 27% remaining. Now, this is shared equally between the two regions because we have symmetry, right? So I'm going to have half of that go in here and half of it go in here. And that's going to give us 13.5% in each of those regions. Okay, so 13.5% of cat weights lie between 64 and 74 pounds. And I can do the same thing now for 99.7%. I can take the 99.7 minus 95%. That's going to give me the 2.7. Yeah, anyway, we're going to have that. We're going to divide it by 2, and then that's going to give us 2.35% on each side. And then we can look at the final one. We know that 99.7% is taken up between the -3 and +3 standard deviations from the mean. We know that the whole curve is 100%, so we have that 0.3% that we can split for those final little tail bits. And so 0.15% over here and 0.15% over here. And when we add all those up together, we should get to that 100%. Okay, a couple last minute details that we want to fit in here are also to define the model, and by doing that we just give a label on the side of our picture that says normal, despite what it may look like. What we're intending is for it to look normal, and it has a mean of 54, standard deviation of 10. The other thing that we might want to add or to think about for making our calculations a little easier is to think of the scale of z-scores, right? So this was 0, +1, +2, +3, -1, -2, -3. And then that will make it a little easier to do our calculations or to think about the regions that we're looking at here. So these are z-scores. Okay, now we're wanting to find the probability that a cat weight, lies between 34 and 74. So if we do a quick sketch of what we're talking about, there was the 54 in the middle. Now 24 34 is 2 standard deviations. So 1, 2 standard deviations away from that middle. So there's 24, there was 54. And we're going up to 74, which is 2 standard deviations above. So we're actually looking at this region in here. And so that by definition, from -2 to +2 standard deviations from the mean, that's going to hold 95% of our data values. So the probability that our weights are going to lie between 34 pounds and 74 pounds inclusive is going to be 95%. We know that. But we can also look at our picture and add the regions up together. So from 34 to 44, that's going to be 13.5%, plus 44 to 54, there's 34%. From 54 to 64 is another 34%, and then another 13.5% from 64 to 74. So that sum will also give us the 95% that we can also recognize just from the definition. All right, so let's find the probability that our weights are between 24 pounds and 64 pounds. Okay, so draw another quick sketch. I think that's where I was getting the 24 from. There's the 54, 44, 34, 24. So that is at 3 standard deviations from the mean, and then 64 is +1 standard deviation. So we're looking for this larger region in here. So the probability that we are going from 24 pounds to 64 pounds is going to be the sum of those regions. So again, I'm looking up at my bigger picture. I'm going to find the probability of lying between 24 and 34. That's 2.35% plus then 13.5% plus 34%. I'm just moving forward until I hit that bound to 64. And then another 34%. And so adding those all together, let's see here, grab my calculator, 2.35 plus 13.5 plus 68, basically. Put those together, and that's 83.85% chance that we have weights that lie between 24 and 64 pounds. All right, so here's one more example. Suppose that y equals n 25 and 5. So that's telling us that this is a normal model, and that we've got a mu of 25 and a standard deviation sigma equal to 5, and that what we're distributing are our quantitative data, right? So that y is going to mean our quantitative data. So quantitative data. All right, and we're going to look for the likelihood that y, our data, lies between 10 and 40, given this model. So I'm going to do a quick sketch here, and I'm going to label it 25 and 5, 25 in the middle. I can go up by 5, so 30, 35, 40. So 30, 35, 40. I don't know what these things are, but I'll just add units as a general label for it. And then 20, 15, 10, 15, 10. And we're going between 10 and 40. So in terms of z-scores, right, that is 3 standard deviations above. So 40 is the equivalent of +3 for our z-score. And 10 is going down 3 standard deviations from the mean. So that's the equivalent of -3. So we're looking for the probability, which is the area. So that shaded area is what we're looking for. And we know, again, by definition, between a -3 and +3, so within 3 standard deviations of the mean, the probability is going to be 99.7%. So that's going to be 99.7% chance. Okay, this is all well and good, but unfortunately we don't always have data values that lie right on 1, 2, 3 standard deviations from the mean. So we're going to end up using most often z-scores and GeoGebra to calculate our probabilities. So recall that a z-score tells us the number of standard deviations a value is from the mean, and we calculate it using the formula z equals data minus mean divided by the standard deviation. And that mean, or data minus mean, the numerator needs to be calculated fully before doing the division, or else you'll have some awkwardness going on there, right? The standard deviation would only divide the mean otherwise. And we leave that as fairly general statements throughout this course because we'll use this same format with all of the different distributions. So we've seen already we could calculate a z-score for the binomial distribution using the expected value of x and the standard deviation of x. Here we're thinking about it in terms of populations of quantitative data. So we're using mu and sigma for our mean and our standard deviation. We're going to be looking at a few more distributions, so we don't want to get too caught up with the symbols, but rather the concept that we're doing a data minus the mean divided by standard deviation so that the z-scores are always how far a data value is from the mean. Okay, and this is a powerful tool for calculating probabilities using the normal distribution. For example, we're going to go ahead and calculate the probability that y is less than or equal to 12, given that we have a normal distribution with a center or mu of 18 and a standard deviation of 2.3. And we're going to go through the steps of this normal model probability calculation. And there's always going to be 4 main steps. And first is to go ahead and draw a picture. And by a picture, I mean of the normal model. And that's going to include both a statement of the model itself, so the definition of it. You're going to show the labeling for the axis, so what are the quantities that you're dealing with, what units are they in. You're going to give a center position, and then you're going to show bounds. And you don't need to do the full 1, 2, 3 standard deviations from the mean. That ends up cluttering a lot of our pictures, and we're dealing often with extremes, so very small and very large quantities, where being too accurate with our scaling will actually take away from the value of the picture itself. So after that, we're going to calculate the z-scores, and then we're going to look at the probability to the left, to the right, or between the bounds in terms of their z-scores using GeoGebra, and then we're going to write a concluding statement in the context of the problem. So those are the 4 main steps that we'll be doing every time with a normal model probability calculation. And you will be graded for all of those steps in a normal model probability calculation. So first step here, draw a picture. So I'm going to start by drawing my sketch. Now this is a sketch. It shouldn't take up your whole page. This is one of many parts of the total process. So you don't want to be too big on this one piece. I want to label it with what it's meant to represent, and it's meant to represent a normal model with a mean of 18 and a standard deviation of 2.3. So I'm going to place that center position. I don't know what these things are representing, so I'm just going to say that these are units. I don't know what they are yet. And then I have bounds. So I'm looking for the probability that y is less than or equal to 12. So I want to position that bound of 12 somewhere in this picture. I know that it'll be less than 18, so I'm just going to stick it over here. So there's my 12. And what I'm trying to find for probability is less than 12. So I'm going to shade to the left of that to show less than. And remembering the shading is illustrating the probability that you are calculating. All right, so that's the basics. Now we want to go ahead and find the z-score for that bound, so for 12. So I want to find the z-score for 12. So 12 minus 18 divided by 2.3. Okay, and I could get my handy calculator. So 12 minus 18 equals divided by 2.3, and that is negative 2.61 to 2 decimal places, always 2 decimal places for our z-score. I'll make a quick note of that. 2 decimal places. And it's also negative as expected since our data value is less than the mean. Okay, now we're going to do our calculation of probability. So we're going to write out our probability statements. The first probability statement we're going to make is the one that is basically given to us in the problem statement. So we're looking for the probability that y is less than or equal to 12. Now, how we're going to go about finding this probability is to use our z-score. And it turns out that if we had taken every data value in our population and converted that to z-scores and showed its distribution, that distribution would be able to give us the same probability information as we get from our data distribution. Okay, so I'm going to show that. So I'm going to have a different distribution, and this is going to convert all of these values to its z-score equivalent. scores. Okay, and so 12, that's actually a z-score of negative 2.61. And it turns out that those densities are going to be the same, namely that these probabilities will be the same. So probability is equal. Okay, and this distribution that we've created by going to z-scores, it has a center at 0 always and a standard deviation of 1. And this is referred to as the standard normal distribution, meaning it's always in terms of z-scores. Okay, so we have a mean of 0 for our z-score. Standard deviation is always going by 1s, and then we have our z-scores corresponding to our data values are filling out the rest of the picture. And this is an important distribution, more historically than necessary right now, because we have a table, a lookup table of z-scores that will correspond with probabilities lying to the left, or in other words, percentiles. And so that's what used to be done as, I don't know, it's still being done in a lot of cases, but especially up to the last 5 years, like before that, we only used lookup tables to find these probabilities, because these probabilities, again, are areas under a curve, and that curve isn't standard. It's not like rectangles that we're adding together. It's much more complex, and so it takes a lot of calculus, actually, to calculate these areas, and so we did not have the computing power historically, and we just go to these lookup tables. And so we could use those lookup tables by converting any of our distributions in terms of this standard normal curve and look it up on one table for every one of them. So it was really, really handy. And that's still used often enough that in an educational setting, it's important for you to see that connection. We're also using z-scores for our probability because it helps us have an approximation in mind ahead of time. I know that 12 is a z-score of negative 2.61, more than 2 standard deviations away. That individual data value is unlikely. I also, by the 68, 95, 99.7 rule, have a little bit of an idea of what that probability is going to be like, right? So negative 2 standard deviations away, if I look at what happens beyond that point in the tail, I have a 2.35% and a 0.15%. So I have a 2.5% altogether past 2. But I'm actually closer to 3 standard deviations from the mean. So I know that this probability should be, less than, well, probably maybe about 1%, maybe 2%, but it's going to be pretty small. And so I already have that in mind when I go to do this calculation. So between having a z-score and having an understanding of the 68, 95, 99.7 rule, I can have an idea of what my probability should be, and I can use that to do checks to verify that I've got the right answers out of our technology. Because sure, we're going to use technology that makes it nice and easy, but it is important for you to still have a way of deciding if the technology has done it correctly for you. Okay. All right. So now we're going to write then the equivalent probability statement in terms of the z-score calculation. So the probability that y is less than or equal to 12 is actually the same as the probability that z is less than or equal to negative 2.61, the 12's equivalent in terms of a z-score. Now to find this probability, we're going to use GeoGebra. It'll make it a lot easier. So I'm going to bring up GeoGebra real quick here, and I have it. There, we'll bring it up over here. So GeoGebra, if you bring it up just from the online interface that is in the menu in D2L, you should get it to come up to look something like this. I'm going to go to probability. So we're going to go to probability. And here it automatically comes up as a normal distribution. Okay, which is what we want. We saw the last time we can scroll through and decide on the type of distribution. We saw the binomial distribution last time, and now we are doing the normal distribution, but it automatically comes up that way. You'll notice it also comes up with a mu and sigma next to that pull down menu that is listed as 0 and 1. That is the standard normal distribution. That is precisely what we want it to be at in order to find the probability. Okay, so we want to enter in a value that is in terms of z-scores to do the calculation. All right, and we want to do less than, so we're going to change this to less than rather than between two values. The shading should have a change as well to illustrate that. And we are looking for less than or equal to, again, in terms of z-scores, a negative 2.61. Okay, and then actually I'll press enter. But what you should see is a picture now that matches fairly closely to what you had in your picture as well. So we have shading to the left. It's at 2.61 for that triangle, illustrating that position of the bound. And then the output after the equals is 0.0045. So I was off. It was even way smaller than 1%. 0.0045. Okay. So again, you can't just rely on breaking up the region, right? If between 1 and 2 standard deviations, there was 2.35%, it's not a nice, symmetric spacing, uniform spacing. We have a curve, and so those probabilities change pretty quickly between it. All right, so 0.0045, and then our last part of this is to write a summary statement or concluding statement in the context of the problem. So for this one, we can expect, actually, let's go with a more standard probability statement. There is about now I want to write this in terms of percentages when I do my conclusions, because that's better understood by my readers most of the time, right? So there is about a 0.45% chance that we get a value that y is less than 12. Okay, I don't have context here, so that's what I'm just going to leave it there. So getting a value that is less than 12. All right, and so that's our basic setup. So we're going to need to include this first part. You need to show this part. You need to show this statement, find the calculated value, and then write up a conclusion. So 1, 2, 3, 4. And the picture that you want to draw is going to be the one related to the context itself. So in terms of the given information as opposed to the standard normal curve. All right, so let's take a look at another one. The number of hours sleep that an average person in the US gets is normally distributed with a mean of 8 hours and a standard deviation of 0.5 hours. And we want to define the distribution. So to define the distribution, remember, we're just going to symbolically summarize that information. We're going to say what is being distributed. These are the number of hours sleep, which we're symbolizing with y. That's going to be equal to n, meaning a normal distribution with a mean or mu of 8 hours and a standard deviation of 0.5 hours. All right. What is the probability of getting less than 9.25 hours of sleep? And we want to show all steps. So our first step in that is to sketch a picture of the distribution. This is meant to look normal with a mean of 8, standard deviation of 0.5. So we're going to put 8 down here. What do these things represent? Well, this is hours of sleep. So hours of sleep, and our bound, the thing that we're doing a comparison with, is 9.25 hours. That is greater than 8. So I'm going to put 9.25 over there. And again, I'm not worried right now about positioning that bound according to a proper scale. It's mostly to show relative to the center, where does it lie, to the right or to the left? Because I want to have meaningful shading. That's what's important to me. So I'm wanting less than 9.25 hours of sleep. So I'm going to shade less than. So that shaded region, remember, is probability. This is what we're looking for. That is our probability, is the shaded region. All right, next step is to find the z-score. So z is equal to our bound or our data value of 9.25 minus the mean divided by the standard deviation of 0.5. Okay, and that's going to be 2.50 to 4 decimal places. A couple of things we can get just from looking at that is we know that this is an unusual value. Unusual, since it's more than 2 standard deviations from the mean. Shading to the left then is shading most of our distribution. It's going to be a lot, right? Because what lies past 2 standard deviations from the mean is going to be similar to the previous problem, right? We're kind of in that same location-ish. It's going to be a very small amount, so we can expect the probability to be close to 1. Close to 1, since we're shading all but a very small portion of our picture. Then our next step is to do the probability statements. So we have the probability of y being less than or equal to 9.25, and that is equivalent to the probability that z is less than or equal to 2.50. So we get that set up. Then we can go to GeoGebra to find the probability itself. All right, so now going back to GeoGebra, what we want to be careful with in GeoGebra is we're just going to be using the z-scores for finding the probability. When we're looking for bounds, we're going to enter in the actual mean and standard deviation for the population. But when we're looking for probabilities, we're just going to use z-scores and 0 and 1 for the mean and standard deviation. So be sure to plug in that z-score here rather than the bound in terms of the data. So we're going to put in 2.5 and then enter, and then check that your picture seems to shade in the same direction first and foremost, that your triangle illustrating the position on the axis looks right, and we're getting that 99.38%. So again, we expected the probability to be close to 1 based on our z-score being so large, and it did turn out that way. So 0.9938 is our probability, and then we want to write up our concluding statement. And so there is about a 99% chance that a person gets less than 9.25 hours of sleep. And this is per night, right? Okay. So that's our concluding statement. I basically follow a template for these probability statements where there is about a blank % chance that, and then look back to the problem statement for the wording for the remainder to put it in context. So you'll notice that quite often in these examples. All right, so now we have another one. What is the probability of getting more than 7.5 hours of sleep? And we also want to show all steps. So this is still in the same context. You'll notice we'll have one kind of starting context, and then we can do a whole bunch of questions related to it. So we're still talking about an hour's sleep. That's, again, not a very good line. There we go. And we're going to do a quick sketch of the probability distribution. We are expecting a mean of, let's make sure I've got this, 8.5 hour, 0.5. There's my 8 hours. This is hours sleep. As a label, 7.5 hours is going to be to the left, so I'll plop that in there. And I am looking for more than 7.5 hours, so I'll be shading greater than. So again, that shaded region is the probability we are looking to calculate. Then we're going to calculate the z-score for that bound or data value of 7.5 hours. So minus 8, the mean, and divide by standard deviation. And that is going to be 7.5 minus 8 equals, divided by 0.5 equals negative 1.00. All right, so we kind of have a good idea of what that should be right off the bat, right? We know with -1 standard deviations from the mean, this is not unusual, first of all, so not unusual. And if we're 1 standard deviation below, then that means we had that 34% already taken off of what was left on that other side. So we're going to have the 34 plus the 34 plus the 13.5 plus the 2.35 plus the 0.15, right? So we can add all those up and that would get us our probability. So from our picture, we know that we're going to have something that's pretty big, definitely greater than 50%, and we should be seeing 50%, half of the picture plus that 34%, since we're down one more standard deviation from that. So we should be getting what, 60, 70, 84%-ish is what we're expecting. All right, so let's go through the actual probability calculation. So this is y is greater than or equal to 7.5. This is equivalent to the probability that z is greater than or equal to negative 1.00. And then we go to GeoGebra for that. So again, we're still in 0 and 1. We don't have to make any changes there. We do want greater than now. So switch that direction. And we want to enter this in as negative 1. Now, sometimes the negatives don't go in nicely, so do make sure you double check before you press enter that it's coming in properly. And lo and behold, yeah, it's pretty darn close to that 84% that we were anticipating just based off of the z-score and our 68, 95, 99.7 knowledge. All right, so this is going to be 0.8413. So to summarize this, we'd say there is about an 84% chance that someone gets more than 7.5 hours of sleep. Okay. And again, we're changing that to percentages when we go into our final statement. Otherwise, all of our calculations should be done using the decimals and decimals to 4 places for our probabilities. That is precisely what's output by GeoGebra. So we're pretty good there. All right, so now what is the probability of getting between 7.5 and 9.25 or 9.25 hours of sleep? Okay. And we want to show all steps. All right, so we need to start by, again, drawing our picture always. This is normal, mean of 8, standard deviation of 5. This is hours of sleep. There is 8. And 7.5 is down here, and 9.25 is up here. Whoop, 25. And so I'm shading the area in between. Now, when we're doing between two values, you need 2 z-scores. So make sure you have those calculations done. Now, we've already done these, right? Z for 7.25. That was done up here. And, oh, I didn't do it for 7.5. There we go. Not the 2.5. 7.5. There it is. We just did that one, and that was negative 1. Now, if we hadn't already done that work, you would need to do the calculations for each of these. And then Z for 9.25. That was done up here. So that was a positive 2.5. Okay, so I have my z-scores. So now I'm going to write my probability statement. So the probability that y lies between 7 and 9.25. This is done with the compound inequality, just like you normally would in a math class. Lowest value comes first. So we have 7.5. Then we do our less than equal to symbol, y less than equal to, and then 9.25. In terms of z-scores, that is the probability that z is between negative 1.00 less than equal to z and 2.5. Okay, and then we go to GeoGebra to find this one. Okay, and we're going between two values, and we're going to have negative 1, which is already in there, and then we're going to 2.5. And then enter. Okay, double check that your picture is showing what you were needing, and then we get 0.8351. Okay, for our probability, and so there is about an 84% chance. So I'm rounding to 2 decimal places when it's appropriate. Sometimes we have very, very, very small probabilities, in which case you'll just take it to a couple significant digits in there. Okay, so there is about an 84% chance that someone gets between 7.5 and 9.25 hours of sleep. Okay. Here's another example. Suppose that IQ scores are normally distributed with an average of 100 and a standard deviation of 15. We want to determine first the probability of scoring below 110. Now, what is important here is that the probability of being less than is actually the same as percentiles. So remember, a percentile, we've seen this before in the context of Q1 and Q3. And this is precisely the percent of data that lies at or below the bound. Okay, so in terms of finding what percentile a value is at, it's the same as finding the less than probability. So same as less than probability. Okay, so don't get too confused if you see the request for the percentile. It just means the less than probability. So find the probability of scoring below 110. All right, so here is our distribution. No matter what it looks like, I mean it to look like a normal model with a standard deviation and mean of 115. So 115. This is 100. These numbers are IQ scores, so I want to add that label. And I'm looking for below 110, so there's 110 below, so I'm shading less than. So there's my picture. Now find the z-score, so my data value 110 minus 100 is my mean, divided by 15 is my standard deviation, and so that's going to be 0.67, okay? As my z-score, this is not an unusual outcome. It's actually quite close to the mean, so I'm going to be pretty close to around 50%. So the halfway mark, that would mean 50% lies below the mean, and so I'm tacking on a little bit more than that. So maybe 60, 70%, somewhere around there. Okay, so the probability that y is less than or equal to 110 is equal to the probability that z is less than or equal to 0.67. And from GeoGebra, let's bring that back up. Okay, I'm doing less than, so change my direction. My z-score is 0.67, so I'll change that to 0.67. Enter. Make sure that the drawing in GeoGebra looks similar to what I was expecting, and so that is 0.7486. So a little bigger than I was guessing there, but not by too much, in the ballpark of what we were thinking. Okay, and so then we have a score of 110 is at the 75th percentile. Okay, and usually percentiles are reported to the nearest whole percent. And again, if you're like really close to 100% or really close to 0%, we might give it a little bit of extra decimal places there, but not usually by too much. Okay, what percentile is a score of 90? So again, this is part B, we're still under this IQ context. So we can draw our normal model. Even if it doesn't look normal, it's meant to be by this labeling. We can tell that. There's our center. Score of 90 is over here. Percentile means less than. Less than percentage. Okay, and so then we need a z-score. That's going to be our data value minus the mean divided by the standard deviation. That's going to be negative 0.67. Oh, okay. Seems a little similar to what we did in the last one, but positive versus negative. All right, and so probability that y is less than or equal to 90, that is equal to the probability that z is less than or equal to negative 0.67. Go to GeoGebra to find that probability. So we want less than still, and we're just changing in here to negative 0.67. And like I was saying before, negatives don't always show up nicely in here. Negative. Okay, let's see if I can get in when it's bigger. There it is. Okay. And is that in the right position? Sorry, flipping back and forth there. And it does look like it's in the right position now. It is showing negative 0.67. The negative 0.67, I'm less than 0, shading to the left. All is good. So that is 0.2514. Okay, so there is about a 25% chance, or a score of 90 is at the 25th percentile. Okay. That should sound a little familiar, because what are the 75th and 25th percentiles? Remember, 75% lies below, 25% lies below. This is Q3. This is Q1. Ha! So we could calculate the IQR based off of this, right? So the IQR would be Q3 minus Q1, which would be that score of 110 minus the score of 90, things like that. So we can start observing some of that stuff going on here. All right, so the next one, what is the probability of scoring above 110? So again, we're going to get that picture. There is 100. This is meant to be normal. Mean of 100, standard deviation of 15. These are IQ scores. And we want above 110. There it is. We're shading over here. Z-score, we've done 110, right? So we can use the same Z-score, 0.67. 0.67. And we want to find the probability that y is greater than or equal to 110, which is equivalent to the probability that z is greater than or equal to 0.67. And we can go back in here. We want greater than, first of all, and we want to change that so we get positive. So 0.67, enter. And then that should make sense, right? Because if we had at less than 0.67 probability was 0.75, or the 75%, then it should make that sense that this is 25%. So aside from a little bit of that overlap issue with the equals in our inequality, we should see these as complements basically. So it's 0.2514. So there is about a 25% chance of scoring above 110. All right. And what is the probability of scoring between 95 and 120? So here's our picture. Normal, 100, 15. These are IQ scores. Place the center at 100. Then our bounds, 95 and 120. Okay, so this is the region that I'm looking at. I'm looking for the probability, the area between 95 and 120. So I need to calculate my z-scores. First for 95, that'll be 95 minus 100 divided by 15. So 95 minus 100 equals, divided by 15, equals to 2 decimal places, negative 0.33. We know it's going to be negative because that 95 is less than our center of 100. And then the z-score for 120. 120 minus 100 divided by 15. 120 minus 100 divided by 15. And that is positive 1.33 to 2 decimal places. All right, now we want the probability. And this is between two values, so we need that compound inequality. So between negative 0. Oops, going to the z-scores too quick. And we're going between 95 for y and 120, which is equivalent to the probability in terms of z-score. So now the negative 0.33 less than or equal to z less than or equal to 1.33. And then we can go to GeoGebra for that. We want between two values. We're going between negative 0. Oh, there we go. I should have left that. Gonna have to shove it in afterwards. 0.33. Okay, and see if I can get in there. The challenges sometimes of, there we go, of the iPad. All right, and then to 1.33. Okay, that looks about right. Press enter, and it looks like 53.75%. So 0.5375. So there is about a 54% chance that or of scoring between 95 and 120. Okay. Let's take another situation. So what if we want to know what the score is at the 90th percentile? In other words, what score is the boundary for the lower 95% or lower 90% of scores? And the percentile we would refer to as P90. So percentile, 90% percentile. All right, so let's take a look at how we would do that and how we would illustrate that, because we're going to do this in GeoGebra, and it's a very quick answer that we'll get to, but we do want to make sure we're showing some sort of work to illustrate our understanding of what the computer system or whatever is doing for us. So the 90th percentile, in terms of a picture, I know this is normal, 115, these are IQ scores, there's 100. And I know that the 90th percentile, because it's greater than the 50th percentile, I know it's got to live over here somewhere to the right of 100. Because when I'm shading below it, that's the 90%. Right? So 0.90 is a decimal. That's the 90%. And then this value on the axis, that is P90. That's what I'm trying to find. So long as I have this labeled in the picture, then my statement that P90 equals is going to be nice and straightforward. So in GeoGebra, to find that bound, now remember what we have here right now is 0 and 1 for our parameters, and that's in reference to z-scores, but we don't want to know the z-score for the 90th percentile. We want to know the actual score on the test. So this is the case where we're going to change from 0 to 1 to the actual mean and standard deviation for the distribution. Okay, so now our scale is in terms of actual IQ scores, and we are looking for less than. And here, notice we have two places we can enter, and we've been entering inside the inequality, so we've done that part of it. We can also enter values out after the equal sign, and that was our area. So we're actually going to put our number 0.9 in that area region. So now we'll know the probability, enter it there, press enter, and then what's inside the inequality portion is the value that gives us that area to the left. So that's going to be 119.22, so 2 decimal places or so. Even 1 would be fine. We can just keep it to 1. Okay, and that's our answer. So a score of 119.2 is at the 90th percentile, meaning that 90% of scores lie below that. All right, so now we want to determine P25 and P75. All right, so we're going to do one picture for each. Don't try and cram together too much in one picture. Here is P25, so normal, 115 IQ scores. There's 100. 25th percentile, P25. That has to lie below because we know we have 25% as our shaded area, so 0.25 lives there. So P25. Then we do the same sort of picture for the 75th percentile. So IQ scores, there's 100. 75th percentile we know is going to be above 100 because we need to have 75% of scores lying below it. So that shaded area is 0.75. That's the probability. So P75. Okay, now we can go over to our distribution. Now it already has mu and sigma as 115, so we know we're in the right type of values. We want the data values, not the z-scores. And we are looking for P25, so we're doing less thans because those are percentiles. and we want to put in the area instead of the boundary in these cases. So we're going to have 0.25 because it always has to be expressed as a probability, which is a number between 0 and 1. And so that's going to give us 89.8 or 88, so we'll just go 89.9. And we have the 75th percentile, change that to 75, enter, and we have 110.1. Now that should look awfully familiar because we already calculated it from the other direction. And that means that these guys, this is Q1 and this is Q3, okay? So now I can find the IQR for our IQ scores. Since I know those 25th and 75th percentiles, IQR is equal to Q3 minus Q1. Third quartile is 110.1 minus the first quartile, 89.9. And then that is going to get us to 20.2, and that's our IQ score. And remember that what we have found is the width of the box of our box and whisker plot. So this is the IQR. So that is the range of the middle 50% of data values. So range of the middle 50% of data values. Okay, that's what our IQR stands for. All right, and what score is the bound for the highest 5% of scores? Okay, so again, draw a picture always to get a sense of what's being looked for. And there's 15, these are IQ scores. Here's 100, and we're looking for the bound for the highest 5%. So highest 5% is gonna lie up here. So that area is 0.05. And we're looking for this Y value to bound that. So that Y value that we have specified, we'll just go back to GeoGebra. Again, we want our parameters in terms of the data values because that's what we want to find here. We don't want to find a Z-score for that position. We want the actual score. And we're going to enter in the area. Now, we could do this one of two ways. We could do the less than, but it's a little easier to follow the picture. So we'll do greater than, and then the area is great. The area that's greater than is 0.05. Okay, so now our pictures are matching up. Press enter, and that should give us a score of 124.67, so 0.7. All right, so that's our IQ score. Now, we could also have thought about it in terms of percentiles, the less than probability. So I could have looked at it from this perspective, and that would have been a 0.95. That lies below it. So the percentage of scores lying below that are 95%. So this Y that we calculated as a percentile is also the 95th percentile. So we could call it P95 because 95% of values lie below that one. So that covers the basics for the normal model probability calculations that we'll be doing. So finding the probability above, below, between two values using GeoGebra and going through the 4 steps. We can also find the bound that is associated with a percentile. Again, using GeoGebra, putting in the area as a decimal that lies to the left or to the right, depending on what we're doing there. We can also find the percentile, which is just going to be the percentage that lies to the left, so less than percentages. And yeah, that's the basics of what we'll be doing here. And it'll get extended to different distributions shortly in the course. All right, so that's it for now, and I will try and stop the video.